Okay, so in this lecture we will look at how to generalize trigonometric functions. So this will rely on our generalization of the exponential function, and we'll also see how many of the properties that we are familiar with for trigonometric functions of a real variable, many of them will also generalize to the complex scenario, and we'll also look at how some properties are new and which come about because you're looking at function of a complex variable. Okay, so the starting point is the recollection that we can think of cosine of x and sine of x when x is a real variable as e to the ix plus e to the minus ix divided by 2 and e to the ix minus e to the minus ix divided by 2i, right? So which is really already using the fact that we have generalized the complex function to include complex variables, and it's really a rephrasing of the Euler formula in some sense, right? So but now we'll elevate x to the status of a complex number and use this as a way to generalize the idea of the cosine of a complex number, right? So we define the cosine of a complex number z as e to the iz plus e to the minus I z divided by 2, and the sine of z to be e to the iz minus e to the minus iz divided by 2i, right? So in fact, so this can be thought of as a generalization of the Euler formula to arbitrary complex numbers. So we have e to the iz is equal to cos z plus I times sine of z, right? So we can immediately see that from this definition both cosine of z and sine of z are entire functions, right? Because e to the iz and e to the minus iz are entire functions. We have seen that the function e to the z or e to the minus z, both of these are analytic everywhere in the complex plane, in the finite complex plane, therefore they are entire. So if you take any linear combination of entire functions, you're going to get another entire function. So cosine of z is an entire function, analytic everywhere in the finite complex plane, and so is sine of z. So if you take the derivative of the exponential function e to the iz, you get I times e to the iz, and if you take the derivative of e to the minus iz, you get minus I times e to the iz. So it's analytic everywhere, and the derivatives are explicitly written down. So using this, we can immediately write down the derivatives of cosine of z and sine of z. So d by dz of cosine of z, you can quickly convince yourself, is actually nothing but minus sine of z, and d by dz of sine of z is nothing but cosine of z according to this generalized definition. So this relation, these two relations are the familiar relations which we know and which we have used from high school days, and so that these relations that we are familiar with pertains to real variables, but they also extend to complex variables. Also, these generalized cosine and sine functions retain their even and odd character respectively. So cosine of minus z, you can verify from first principles from the definition, is the same as cosine of z, and sine of minus z is minus sine of z, right? So there are several useful identities which also generalize, and all of this goes back to the definition of cosine of z and sine of z. You can directly derive all of this, right? So for example, sine of z1 plus z2 is equal to sine of z1 times cosine of z2 plus cosine of z1 times sine of z2, and cosine of z1 plus z2 is equal to cosine of z1 times cosine of z2 minus sine of z1 times sine of z2, right? So this is something that can be verified by just directly plugging in this expression for cosine and for sine, these two expressions, and then working out the algebra, and can show that indeed these identities carry through. So the periodic nature of sine and cosine functions also generalize, so which you can actually directly see from plugging in here these expressions. Sine of z plus 2 pi is the same as sine of z, and cosine of z plus 2 pi is the same as cosine of z, no matter what complex number z you're looking at. But we also have these relations: sine of z plus pi is minus sine of z, and cosine of z plus pi is minus cosine of z. And also we have the relation sine of pi by 2 minus z is equal to cosine of z. This also generalizes: cosine of pi by 2 minus z is equal to sine of z, right? So these identities can also be worked out, using these identities, right? So this is something that you can check for yourself, that these are all direct consequences ultimately of the definition of sine of z and cosine of z, right? So these are familiar identities, but what is important to emphasize is that they carry through in exactly the same form even when we allow z to be a complex number. Now if we set z1 to be z and z2 to be pi by 2 minus z, so if we add these two, of course it's just pi by 2. So sine of z1 plus z2, which is pi by 2, sine of pi by 2 is sine of z1 plus z2, which is the same as sine z1 cos z2 plus cosine z1 sine z2, which is sine of z times cosine of pi by 2 minus z plus cosine of z times sine of pi by 2 minus z. But cosine of pi by 2 minus z is sine of z, and sine of pi by 2 minus z is cosine of, so this should be cosine of z. Sine of pi by 2 minus z is cosine of z, and from which we immediately get the identity sine squared z plus cosine squared z is equal to 1, right? So this is a generalization of the familiar identity which we have used a lot. So there's a couple of useful identities which we can derive, again starting from the definition. So cosine of z is just e to the I z plus e to the minus I z divided by 2. So you can write this as, write z as x plus iy, so you get e to the ix times e to the minus y plus e to the minus ix times e to the y. Then if we expand, so you get cos x plus I sin x times e to the minus y plus cos x minus I sin x times e to the y, whole thing divided by 2. And then you collect terms carefully, so you have cosine of x times e to the y plus e to the minus y divided by 2 minus I times sin x times e to the y minus e to the minus y divided by 2. But then we immediately see that e to the y plus e to the minus y by 2 is nothing but cosh, the hyperbolic cosine of y, and e to the y minus e to the minus y divided by 2 is hyperbolic sine of y. So we get this identity: cosine of z is cos x hyperbolic cosine of y minus I times sin x sine hyperbolic of y. Right? We can derive a similar identity for the sine function, which we state and allow you to verify yourself. Sine of z is sin x hyperbolic cosine of y plus I times cos x hyperbolic sine of y. So these identities, right? So you can also think of these as an explicit expansion of these complex numbers. After all, cos z is a complex number, sin z is a complex number, and so you can think of these as expressions for the real part and the imaginary part, right? And these expressions will also allow us to investigate bounds on sine of z and cosine of z, right? So when we're working with trigonometric functions of a real variable, so we know that both sine and cosine functions give you numbers which necessarily must lie between -1 and +1. They can never get out of this this bounded region. But on the other hand, when you're working with complex numbers, we see that in fact they are unbounded from above, right? So mod of cosine of z squared is just the real part squared plus the imaginary part squared, which you expand and then you collect terms, and then you use the identity that cosine squared of y is 1 plus hyperbolic sine squared of y, so plus sine squared of x times hyperbolic sine squared of y. Then you collect terms again, so you have cos squared x comes out, then hyperbolic sine squared of y times cos squared x plus sine squared of x, which is just 1, so you get cos squared of x plus hyperbolic sine squared of y. And similarly you can show with a similar type of algebra that mod of sine z squared is sine squared x plus hyperbolic sine squared of y. So we see that since hyperbolic sine of y can take arbitrarily large values, if y is non-zero, meaning it's a complex number, it's a genuine complex number, then indeed the value, the modulus of cosine of z and the modulus of sine of z can be arbitrarily large, right? So they're unbounded. But we can also write down these lower bounds. After all, mod of cosine of z squared and mod of sine of z squared, is seen to be the sum of two squares. Therefore, each of then mod of cosine z squared must be greater than or equal to sine squared of x, and mod of cosine z mod of sine z squared is greater than or equal to sine squared of x, and mod of cosine squared is greater than or equal to cos squared x. Sometimes these inequalities are useful to put these kinds of lower bounds. Okay, so what about the zeros of sine of z and cosine of z? We know for sure that this function is periodic and it keeps hitting 0 as you go along the real axis. So it turns out that there are no other zeros. All the zeros of these functions are located only on the real axis, right? So one way to see this is mod sine of z squared is the sum of these two squares. If sine of z is 0, the only way that can happen is if the modulus itself is 0, and which can happen only if each of these positive numbers which add up to form this number are separately 0. So sine of x must be 0 and sine of hyperbolic sine of y is 0, and which immediately means that y must be 0 and sine x is 0, tells you that it can happen only when x is equal to n pi, where n is some integer, right? So these are the familiar zeros of the sine function. So by generalizing the sine function to allow for complex variables, we don't find any new zeros. The zeros are still those on the real axis. And likewise, mod of cos z squared, if this is going to be 0, then cos squared of x must be 0 and sine hyperbolic squared of y is 0, and therefore y must be 0 and cos x is 0 implies you again get these familiar zeros. So z is equal to n pi plus pi by 2, where n is an arbitrary integer. So using these definitions for the sine and the cosine, we can also find we can also define other allied trigonometric functions. So we can define tan of z to be sine of z divided by cosine of z, cot of z to be cosine of z divided by sine of z, secant of z to be 1 over cosine of z, and cosecant of z to be 1 over sine of z. Now these functions are also analytic everywhere except those points where the denominator becomes goes to 0, right? So tan of z is analytic unless cosine of z is 0, and which we have seen happens at these points z equal to n pi plus pi by 2. They all lie on the real axis. So these are the singularities of these functions. Tan of z and secant of z, both of these are analytic everywhere except at these points. Z is equal to n pi plus pi by 2, where n is some integer. And again, cot of z and cosecant of z, both of these functions are analytic everywhere in the complex plane except at these points on the real axis where sine of z has a 0. These are the points z is equal to n pi, where n is an integer. So when these functions are analytic, their derivatives exist, and in fact they have these same familiar expressions which we are used to from considering these functions of a real variable. So derivative of tan z is going to be secant squared of z, according to the way we have defined it. Derivative of cot of z is minus cosecant squared of z. Derivative of secant of z is secant z tan z. Derivative of cosecant of z is equal to minus cosecant of z cot z. All of these identities just carry through directly at all points where these functions are analytic. Okay, so that's all for this lecture. Thank you.